Hello again and welcome to the second part of this case study about social life cycle assessment. For those who did not watch the first video, my name is Marie Loubert. I'm working at Green Delta and this is a case study about a hooded sweater. After studying the environmental impacts using EcoInvent in the first part, we're now going to dive into the social impacts of the hooded sweater, and for this we're going to use PSILCA. The report and model for both of the LCAs are available at openlca.org. I will put all the links in the description. The reports are free of charge, and you can also access the model for free if you have the relevant databases. So for this case specifically, you need the PSILCA license. You can find more information about this database and how to purchase it on OpenLCA Nexus if you are interested. PSILCA is an extensive social database developed by Green Delta, so if you have any question or any comments about it, do not hesitate to contact us directly at psilca.greendelta.com. We are going to follow the same structure than previously. So starting with the short introduction, going through the 4 ISO blocks, and finally finishing with some limitations and conclusions. So before starting, just a bit of context. We saw in the first video that India is the biggest producer of organic cotton globally. However, it does not stop at the production of the raw materials, since the sector of cotton garments in India is also quite developed. This large supply of clothes comes at very competitive prices, which makes it very attractive for European retailers. Unfortunately, these low cost of products are not without consequences, as they come at the expense of the workers' conditions generally. Indeed, the literature reports declining wages of workers over the past decades, but also cases of child labor, discrimination against women, and the list goes on. So today we will see how to use social LCA to evaluate the social impacts of a product along its supply chain. So starting with the goal and scope. So the goal of this LCA is to map the social impacts of the hooded sweater along its life cycle. This study was also carried to guide LCA beginners through social studies, specifically using the PSILCA database. So a focus on the methodology will be made all along this presentation. The functional units remain the same than before, so 1 organic cotton 2XL hooded sweater with a weight of 750 and used for a year. The scenarios, some scenarios will be studied regarding the use phase, different from the environmental study. So this time we are going to have a base case where the user washes the sweater himself or herself, another scenario with the laundry service, and finally, a scenario where the washing is done by a housekeeper or any similar worker washing the sweater on your behalf at home. Here is the system boundary of the system. So for those who watch the environmental part, it's very similar. The adaptation that we made for the social study is that we modified the distribution stage. So now it focuses a bit more on the retailers themselves, so it is based in Germany, and it does not only model the transport from India to Germany, but also the retailing part. Some details about the tools and methods. So we still use OpenLCA, but this time the 2.0 version. We use the database PSILCA version 3.0, and we use the LCA method, social impacts weighting method. Here is an overview of the assumption we made for the study. For the manufacturing, we stay with the same consumption that before. So 94 of cotton, 3 of polyester resin, 3 of brass zipper. For the distribution and retail, which is entered by German retailers, we assume a price of the retail sweater to be 40 euros. For the use, we are still using a Type C machine with a maximum load of 6 kilograms. The sweater is washed 52 times in total at 60 degrees and is air dried, and this is not going to change. And 3.8 kilograms of clothes are loading in the washing machine every time. Finally, regarding the end of life, it is assumed that the product is treated as municipal waste, which implies that there will be no reuse or recycling of the sweater, like previously. Let's move to the life cycle inventory. The very first step of the life cycle inventory is to model a foreground system and to link it with background data from the PSILCA database. Once this is done, we will see how to add social indicators to the system we created. So to model the foreground system, you will begin with data collection to create the structure of the life cycle stages. In other terms, you need to collect the inputs of all the relevant processes of your case study. Since we already did this data collection for the environmental LCA, we are going to take the same structure, so remember the circular structure, centralized, and to adapt it to the social case. There are, of course, other ways to collect data for this step. Social and environmental studies found in the literature, for instance, can provide life cycle inventories, but also product LCA databases, such as EcoInvent. The best case, of course, would be to have primary data to model the foreground system. So now that you have all the inputs, each item must be associated to a representative sector in order to link the model to the generic data available in the database. The most common classification of economic activities are given by NACE, documentation for Europe, NAICS for North America, and ISIC for the world. PSILCA, which we are using, follows the economic sectoral classification in place in each country, provided by AOR. Once you have the name of the sector, you may have to choose between commodities and industries in OpenLCA. The sectors inside the folder Industries represent the whole industry sector, which can provide more than one commodity. For instance, the industry mining of metal ores can produce metal ores, but also steam and other byproducts. On the other hand, commodities represent the average for the provision of the good from different industries. So common commodity sectors are usually chosen for product social life cycle assessments, provided they are available, of course. So it might be that you have to choose industry as a proxy. In this regard, if a specific sector is missing, you will have to choose a proxy for it to bridge this data gap. There is no straightforward way to handle this limitation, but there are several alternatives that you can explore. You can choose a similar sector. For instance, the sector I chose for brass was copper ore, as it is the main component of this material. You can also find a broader sector that includes your sector. In this case study, road transport did not exist, so I used other transports in India, which group all of the transport not represented into the other categories. And alternatively, the sector from neighboring countries can be chosen. In the end, it is part of the researcher's choices and assumptions to choose a proxy which is as representative as possible for the missing sector. This is what the process looks like. So you created the structure at the very beginning. This is my manufacturing process or stage. We have the economic input linked to an economic sector. related to a country and commodities or industry, and quantified with the amount in United States dollars from 2015. Now, if you are used to environmental LCA, there are a couple of adjustments that you need to make when you carry a social LCA. First of all, there are some flows that are commonly modeled as outputs in environmental LCA, such as waste flows, which are often modeled as input services in social LCA using waste-related sectors from PSILCA. So here you can see the end-of-life process where the only input is a waste disposal sector from Germany. So this was taken as a proxy for the waste management in our case study. However, if you have the relevant data and you can model a specific waste treatment process for the relevant country, for the relevant sector, and that you have the data to add social indicators to it, you can of course model your own sector or process. The waste treatment process can be modeled with material flow logic or opposite direction approaches, as always in OpenLCA. Another common difficulty faced when modeling the waste flow is the absence of a specific waste sector, as it is only available in a limited number of countries in PSILCA. It was the case for the process manufacturing, as there is no waste sector for India in the database. So after doing some research, I learned that waste collection in India was mostly driven by the informal sector, with waste pickers extracting value from household or industrial waste, and that 90% of the cost of waste management actually came from the collection and transport of this waste. So this service was modeled as road transport, using the PSILCA sector or the transport, mostly because there was no specific road sector for India in PSILCA. Since the health risk from collecting organic cotton waste fabric are pretty low, the results are not expected to be significantly impacted by this proxy. So this is the solution that I chose for this case study, but of course it is very study specific. So another specificity is the modeling of transport. Some modification of the environmental model were made to fit the transport sectors available in the PSILCA database. The distribution is now modeled with road transport, represented here by other transport, from the manufacturing site to Chennai, an Indian port, and the product is then shipped from Chennai to Germany. So the input shipping that you see here. Theoretically, the country responsible for the transport is the country that owns the means of transport. However, in practice, the person carrying the study should try to find the most representative journey based on the sectors and data available from PSILCA. This is what I try to do here. Now that we modeled the forecount system, we need to understand and evaluate site-specific social challenges. For each social indicator selected, we need to find a raw value to evaluate the risk and quantify it with the activity variable that we chose. These indicators will be integrated as outputs of our processes on OpenLCA. The very first step is to prioritize where to investigate. In this case study, a screening was carried by looking at the most intensive activities in the supply chain. These activities are the PSILCA sectors that are inputs in the foreground model and that show the highest market prices. These findings need to be combined to sector literature review. For this case, the sector investigated more precisely were cotton textile in India and shipping in Germany. Here you have an extract of the social aspects for the sector cotton textile in India. To find this information, you have to open the social aspect tab on OpenLCA on the PSILCA sector that you are interested in. All the indicators that are marked as high risk or very high risk, as you can see here, can be a starting point for your research. Now, for the actual collection of raw values, primary data collection should be prioritized if possible. For this study, secondary data was used, which was sector-specific, and it was more precisely a report from Thera Foundation and another one from ILO, so the International Labour Organization. It was a case study about the garment sector in India, which provided information for some of the indicators. If site-specific data is not available, or in order to cross-check data, you can investigate open-source databases provided by organizations such as the World Bank data, the ISO-Stats, or the OECD database. These are only a couple of examples. Try to never rely on only one source. To complete the collected data, it is possible to take proxy sectors from PSILCA, from relevant PSILCA sectors. You can see here the proxy sectors chosen for this study, with a different proxy sector for the two use scenario. So for the laundry, it is considered another services in Germany, while for the use scenario housekeeper, we took as the proxy the services for private households. Then, the raw value of each indicator found is attributed to a risk evaluation. For this study, I only used already existing indicators from PSILCA, so I could access the risk evaluation directly in the software. For that, you go in the Indicators and Parameters folder in your navigation pane. Then you go to the folder Social Indicators, you select the one that you want, and you will find on the general information an explanation about the unit, and on the same tab, the risk evaluation. So to give an example, I found in the literature that the trade union density in the garment manufacturers in India was about 5%. Since we are between 0 and 20%, this indicator will be set as very high risk in the process manufacturing. If you need more information about the units or more generally about the methodology of the indicators and their risk evaluation, you should refer to PSILCA documentation, and here it is the version 3.0. You will find there an extensive description of every indicators. Overall, you have here an extract of what it looks, the output. So it's only social flows, as you can see. So now that we know that the risk associated to the trade union density is very high risk, we can add the relevant social flow in the output of the process. And here it was the manufacturing process. It can be also relevant to create a new indicator, very specific to your study. The guidelines for social life cycle assessment of products and organization is a document from the UNEP and CITAC initiative, which gives a recommendation for the creation of reference scales if it is relevant for your case to create a new indicator. More generally, these guidelines are very useful when carrying a social study, so if you didn't know it yet, I really recommend that you take a look into it. So the last step to add the social indicators is to express them, so to quantify them with the activity variable. So here, the quantification of social indicators was made with the worker hours, which is defined by the formula that you have just here on the slide. So worker hours themselves are expressed in hour. The labor costs, the unit labor costs are dollar per dollar. The mean hourly labor costs are dollar per hour. And finally, the price of the product is expressed in dollar. Let's take a look into how to calculate it in practice. So here I show two ways of calculating the activity variable depending on what data is available. For instance, for manufacturing, a unit labor cost of 3% was found for the textile sector. The mean hourly labor cost could be estimated from the wage of workers and their average weekly hours of work. And we could combine these two elements with the price of the product And then you finally get the worker hours here. So for the process manufacturing. Now, there can be also other ways. So an alternative way is to use the worker hours per dollar of output of representative PSILCA sectors. You can find that value either in the amount of outputs or in the activity variable column in the social aspect tab. And it will be, of course, the same in the outputs or in the social aspects that we saw earlier. This method was used for the distribution and the use stage. So here you have the example with the distribution retail, but it was the same for the use stage. So we used the representative PSILCA sector that we defined earlier. So the proxy sectors just a couple of slides before. So with distribution and retail, it uses the wholesale trade in Germany as a proxy. So you have to multiply this value by the market price of the output, the main output of the process, and you get also worker hours. Overall, this is what it looks like. So you have your full process over here. So from the beginning, we chose the structure for the foreground system that we mapped directly to some economic sectors from PSILCA by choosing a country, by choosing exactly which economic sector was representing the product, and quantifying it with the market value. And then we added to this the social outputs over here, and of course the quantitative products of the process, but apart from that only social flows, for which we picked a risk associated to a raw value that we found and quantified by the same activity variable. Let's explore the impacts of the product. So, I first calculated the result with the social impacts weighting method, and then I used the contribution tree tab in OpenLCA to assess the contribution of life cycle stages to every impact category. So you can see that the impacts mostly come from the manufacturing stage in blue. For most of the impact categories, it is the most significant life cycle stage. But that also for many indicators, the rest of the impact are shared between distribution and the use stage. And end of life is barely present in the impacts for most of the categories. So this is what the contribution tree looks like for the impact category fair salary, for instance. So every time you unfold a process, you can dig deeper into the supply chain, which will allow you to map any recurrent risk in your model. So I deduced from this hotspot analysis that in the manufacturing stage, the most contributing elements are the cotton textile sector in India and the direct impact from the process itself, so from the process manufacturing. The direct impacts are those caused by the social risk in the process. So they are the social indicators that we added to each stage during the life cycle inventory, so the social flows in the outputs. On the screenshot here, it is clear that the direct impacts predominate because you can see very little contribution from the inputs, which means that a large part of it is actually in the process. So from the social flows that we put in the output part. For the distribution and retail, the shipping sector of Germany predominates for many impact categories, but the direct impacts also contribute significantly. So again, the social flow that we added to the process, distribution and retail. Finally, for the use stage, the most contributing elements are the sectors of electricity and the chemical manufacturing. In the base case, the use stage does not include any social indicators since there is no worker involved, which is why the impacts only come from the supply chain. Let's take a closer look to some of the impact categories for which we had more complete and specific data. For the fair salary category, about half of the impacts come from the garment manufacturers. This is due to the low wages reported in this sector, notably as they are lower than the living wage. Some regions in India have a legal minimum wage lower than the living wage, which is the case of Maharashtra, and some regions don't even have a legal minimum wage. The direct impacts of the distribution stage represent also a significant part of the total impacts, which you can see here. This is due not to the salary themselves, because they are quite high, but it is due to their value compared to the living wage, because in Germany the living wage is quite high, which reflects a high cost of living, and in PSILCA, for the moment, it represents a risk even though the salary is above the living wage. It is also the case for the sector of electricity in the use stage, here, as it is based in Germany and therefore with the same living wage. For the gender wage gap, almost all of the impacts come from the garment manufacturing side. Indeed, the Fairware Foundation report documented a gender gap of 39%, which represents a very high risk. More generally, they report inequalities in the access to education and to the workplace, which results in the segregation of women to unskilled activities such as basic agriculture, elementary services, and handicraft manufacturing. Moreover, managerial positions are predominantly given to men, which explains the high gender wage gap in the garment sector. For the trade unionism category and the value added, let's look a bit deeper in the impacts. So, we saw earlier that there's a very low trade union density in the Indian garment manufacture, which is represented in the direct impact over here. But as you can see, the larger part is from cotton textiles. So, cotton textiles manufacturers have a low density of trade union, which is a bit below 20%. The high input of cotton fabric in the process manufacturing justifies why cotton textile contributes so much to the impact. As you can see, it's over 70%. Within the sector of cotton textile, the direct impacts here and the input from leather products are recurrent issues. Finally, manufacturing also predominates in the value-added category, 96%. It is due to the very low value added in the sectors of cotton production, textiles manufacturing, and garment manufacturing, which is partly why their products are so attractive for European retailers. This low added value is made possible, among other things, by the low labor costs that reflect on the low wage of the worker. Now let's take a look into the scenarios regarding the behavior of the user. So the base case is an internal use. This one is an internal use at home, so there is no worker involved. The second scenario is a washing by a laundry as a service. The third scenario is a washing by a housekeeper or any type of worker who would wash the sweater on your behalf at home. So as you can see in the relative results displayed here, the two alternative scenarios show higher impacts than the original one in all of the impact category. It makes sense since they include additional social outputs in the use process. The laundry and housekeeper scenario are the two worst options in about the same number of categories, but if you closer look at the variation, housekeepers show particularly higher risk compared to the other scenario. It is the case for men in the sexual labor force, for instance, over here. which is due to the fact that the portion of men in the sector other services at home is quite low. Overall, we can say that the impacts of these products are sensitive to the behavior of the user. We are going to finish with some limitations and conclusions for this study. So, similarly to the environmental study case, the first limitation is relative to the data quality. Indeed, since it is a fictional case, there was no primary data to build the model, which is a major limitation to the interpretation of the results. In addition to that, some pieces of data found in the literature were left of the model as they did not fit in any existing indicators. Consequently, new indicators could be developed to include sector-specific issues in a more comprehensive manner. Finally, additional research could be done to evaluate the impact of the product during the use phase. For now, we only modeled the potential social risk if a worker was washing the product, but we did not look into potential, for instance, health effects when the user washes the sweater, for instance, because of chemicals or because of any risk from using the washing machine. So what can we conclude from this study? So first of all, a large part of the potential risk lay in the manufacturing stage, even though the distribution and the use stage also share some impacts. Knowing that, a recommendation for German retailers would be to choose a manufacturer which performs socially responsibly, particularly in terms of working condition. So, for instance, being careful with the weekly hours of the manufacturing site, paying attention to overtime hours, to the trade union density, and to the sector wage. Regarding the use stage, we saw that washing the sweater yourself showed the lowest social impacts, so this would be the main recommendation that we can derive from the study from the user perspective. Here you can find the references used for this presentation. So this is all for this whole OpenLCA case study. Thanks for watching, and feel free to contact me or any people in the Green Delta team if you have any question, or to use the comment section of this video.